Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future, binge watching before the exam. So today we are going to finish the part hopefully on data modeling. And I'll show you the link between validation schemas on the one hand and data frames on the other hand. And then if time permits, we'll move on to the next section, which is map reuse. But before that, I would like to first ask you a question. I need to apparently click on here, because we are going to rehearse HBase a little bit, because it's a tough lecture. It's very complex. There's already been a lot of questions in the lecture. I've heard there's also be a lot of questions in the exercise sessions. And I'd like to take some more time to review and rehearse a little bit the material, which is also yet more opportunities to ask questions right now. So let's just refresh and test a little bit your knowledge here. So my first question of the series to you is, you remember the key values in HBase, where are they stored? On disk as immutable file structures for durability, or in a write-ahead log to prevent loss of recent data, or in the mem store for the fresh data, or in caches containing key values that are already persisted in disk, but you have a copy in the cache for faster retrieval. Multiple answers possible, of course, multiple correct answers possible. So let me start revealing the answers. I think I probably have a magic button here. Yeah, just click here and that should show the answer. Ah, that's strange. It doesn't show the actual responses that you give. I have no idea what everybody answers. I can tell you that all answers are correct. That's in any case. Yeah. And I should figure out why it's not actually showing the answer. Let me look actually, maybe I can find it on the website. And otherwise I'll just let it go. So if I click on where they are stored, can I change something here? Show responses live, maybe, oh yes, now you should see them. No, you can't. I can see them. So I can see that it's mostly all even, right? There's an even distribution, which you cannot see here, but at least I can see them. I'm still oh yes, now you can. You see? So that is the distribution, and just because I have my mouse on one of them, yeah. So they are all correct. All of them are perfectly correct. So this is great. So yes, they are stored, of course, on the disk for the very long term in H files, and they are stored in a write-ahead log. That's for the recent data we're afraid to lose. Then it's in the mem store for fresh data, in caches to ensure that we can make the retrievals faster if we frequently access them. Okay, so that was question number 1. Who remembers what is a key value in HBase? What is there in the key of a key value? Yes? So the column family is one thing. What else in the key? The row ID, yes, absolutely. Anything else? The column qualifier, that would be the name of the column in addition for the family. And anything else? Yes? If it's deleted or not, that's the tombstone. And one last thing. The timestamp, exactly the version. So yes, the row ID, the column family plus qualifier, and the timestamp, and the yes or no, has it been deleted. All right, so thank you very much. That's indeed the key value. Let's go to the next one. I told you we are seriously going to rehearse. So now, which ones of these statements are correct? The first one is that in an H file, the key values are sorted lexicographically. Statement number 2, in a write-ahead log, the key values are sorted lexicographically. Statement number 3, H files have fresher, so more recent key values than those in the write-ahead log, or is it the other way around, that the write-ahead log has fresher key values than in the H file, right? So the key values, basically, they identify one specific value in the table, and the row ID gives you the row, and the column qualifier and the family give you the column. And then the timestamp handles multiple versions, and the tombstone allows you to say that it has been deleted. All right, now many of you have answered already, so let's see the answers. So maybe I can first, on my secret administration panel, I can show you what you have answered. And normally, after a few seconds of delay, as happened last time, you should see them. Yes, you can. So what did you say? Well, there's two answers that you really liked, the first one and the fourth one. So let's look at the first two. In the H file, indeed, everything is sorted lexicographically, right? And this has to do with the fact that the H files have to be written in their entirety in a single go. You just write the H file, potentially with huge numbers of key values, and they are sorted. They need to be sorted because we need to be able to quickly find them, right, with the index and the binary search, so they are sorted. In the write-ahead log, does anybody remember in which order they are sorted if it's not lexicographically? Yes? You said the timestamp? That's almost the correct answer, more precise than that. Is it really the timestamp in the key or something else? Yes? The time of insertion. So your answer was basically correct, but I just want to make more precise that the time of insertion, so the timestamp of insertion, does not need to be the same one that you have in the key. I'd say a few words, but so that's a almost fully correct answer and a fully correct answer. A few words about why I'm saying it's not necessarily the same thing at the timestamp in the key is that the timestamp in the key can be user controlled. The user can force a specific timestamp when they insert a value. So it's already advanced users that would do that. The regular users wouldn't even touch the timestamps. They would just not even use the versioning system. But a user can basically create a key value somewhere, so insert a value in a cell, and then they can kind of insert a value in the past. So they can basically say, I want it to be version 4, can even just be an integer or something. So they have control over that. So the timestamp in the key might not be the time at which it was inserted because of this. So that's a small subtlety, already an advanced subtlety. And so indeed, in the write-ahead log, they are sorted in the order in which they were inserted, because the goal of the write-ahead log is to just keep a backup of the recent data just in case we lose the electricity and the mem store goes down, right? So since it's the order of insertion, it's just appending. Whenever you have new modifications, you just append to the write-ahead log, right? That's why it's called a log. And then if it crashes and we need to restore the recent value, we just play the log by just going through the order and adding them back to the mem store when we restart the machine. For whom is this clear? Right? Very good. All right. Then that takes care of the first two. And then we have the other two. So you think that the fresher values are in the write-ahead log than the H files, and this is correct. This is correct. The H files, these are the fossilized data, right? So that's the data that was already flushed and compacted long ago that used to be in the mem store, and it used to be in the write-ahead log. But once it's been written to an H file, you don't need to keep it in the log anymore, right? So the write-ahead log is really the very recent data that we're afraid of losing, because otherwise it's only in the memory of the machine. That's the fresh key values. Who is with me? Right? Very good. Okay, so that's good. So you see there's a lot of questions, but you understand what's going on, right? So most of you get it correct. Okay, then I'm going to move on to the next one, which, or maybe I think, yeah, when I click, you show that this confirms the majority was correct in here. So let me switch to, oh, what's going on? What is going on? Let me reproject. These are just a few. There you go. Now I see it here. Let me see if I project it. Yes, that works right here. So you can already see it in the Menti, but I will also reproject on the screen. Okay. So what is this question? Very scarily long, but let's go through it. So H files are the physical files that store the old key values, right? The ones that store the older key values in sorted order. Now we know it's lexicographically sorted. So first the row ID, then the colon family, then the colon qualifier, then by decreasing timestamp, by decreasing version. But my question here is, how are they modified? So the user connects to HBase, they put some value in somewhere, they delete some value, they replace a value with something else. What happens with the H files when users do that? So I have 5 propositions. Proposition number 1, every time a value is inserted, modified, or deleted, then the H file corresponding to a store, remember the store that's region, colon, family, right? These are the zones we partitioned like a wedding cake. So every time you modify something, immediately you just update the H file in place. So every time you update the H file. Proposition number 2, H files get created every time the write-ahead log of a region server becomes full. So the log is growing too big, and so we are going to just create an H file every time it becomes full. So only based on the write-ahead log. Then proposition number 3, an H file is created through a flush every time the mem store, which stores the most fresh key values from a store, is full. So you flush the mem store when it's full. Proposition number 4, every time a value is inserted, modified, or deleted, a new entry is appended to the H file at the end. So you don't modify the value in place, you just append at the end of the H file that corresponds to a store. Proposition number 5, an H file can be created through a compaction by merging smaller H files. So these are 5 different ways that an H file could be created. I can give you a precision that maybe I should make the second proposition a bit more precise. When the write-ahead log becomes full, we sort the write-ahead log, and that's the intent, right? It's created from the write-ahead log when it's full. So many of you have responded. And now that I found the trick to make the questions appear, because I used to let the answers be shown directly, but then you don't have time to think, right? Because you already see the other answers. So this is the reason why I try to hide it in some way. And now, normally, you should see them appear. And we have 2 popular answers. And these 2 popular answers, I think, are correct. So if I click, normally, I should also be able to show you the correct one. So yes, number 3 and 5 are correct. You remember, it's the flush and compact. We flush, we compact, we flush, we compact, we flush, we compact. These are the 2 ways that the H files are created, right? We always flush or compact to create H files. Answer number 1, who agrees it would be extremely inefficient? Right? Extremely inefficient. Very good. So we cannot do this because otherwise it would take so much time every time. The whole system would be bound by latency and the user would just have to wait for such a long time. So this is why we instead use batch processing, and the batch processing idea is to accumulate in the memory, and when the memory is full, then you flush them, right? So you then write entire H files at once, but not every time a value is modified. So this is why the first answer is incorrect. The second answer, I needed to add the precision, because if you want to be very picky, it is true that a long write-ahead log might trigger a flush, but it's still a flush that happens. It's not taken from the write-ahead log. But technically, saying that the write-ahead log is full is close to saying that the mem stores are full, right? It's kind of growing at the same time. If the memory grows, then the write-ahead log grows too, because you create key values, right? So if that were in a quiz, answer number 2, you might have been able to argue in an email that one technically triggers a flush, so it's not entirely incorrect, right? So that's not entirely wrong. It's just that it's very important to understand that in the mem store, the key values are pre-sorted in a tree structure, and so it takes linear time to flush to the mem store, right? Otherwise, it would be n log n if we needed to sort the write-ahead log. Who agrees? Right? Very good. Number 2, of course, it's correct that you just flush to a new H file when the memory is full, so that's the most recent values. Number 4 is not correct. That would be the write-ahead log when you append, right? Do you agree? The fourth one, it's the write-ahead log that you append the most recently inserted key value. Who agrees? Right? Okay. And number 5 is correct. Number 5 is this idea that at some point, if you keep flushing, you have too many H files. And so you just compact them. There's minor compactions and major compactions. You just reduce the number of H files. But of course, the cost to pay is that they grow larger and larger. So you get fewer, larger H files. Does anybody remember what happens to the H files at some point where they got compacted so much that there's way too much data in the region? What happens then? Starts with yes? We split the region, and then the H files are going to be split as well, right? Who remembers that? Right? Very good. Okay, so you did really well, and the majority is correct, right? There is normally nothing that I haven't said in the lecture or that is not in the textbook, right? So this is all, I was very careful to not introduce new things to confuse you more, right? Okay, so that takes care of this one. So then I'm going to move on to the next one, which is, what is the difference between the mem store and the block caches, right? You can also find the block caches. One of them is called the block cache with capital B, capital C, which is a very original name. But there are several kinds of them that I don't want to confuse you with, right? So what's the difference between the mem store and the block caches? Answer number 1, not at all. There's no difference at all. This is exactly the same thing, right? The mem store is a block cache. That's the block cache. Number 2 is there's no difference. So the first one says they are the same and they store the most recent key values. The second one says they're also not different, but slightly different. The answer number 2 says they both store H blocks of key values that were recently accessed from the disk. Okay. Answer number 3 says there is a difference because the cache stores the recent key values, while the mem store stores the key values frequently or recently accessed from disk. That's answer number 3. And answer number 4 says they are different too, but the other way around. So the mem store stores the recent key values, and the cache stores the key values frequently or recently accessed from disk. Disk meaning the H files, the older values. So let me see the answers that have accumulated. So if I click here, will we see them? Don't have the magical formula for that? We should, normally. It's connected to the internet, right? But I can tell you what I see. I see an overwhelmingly majority answer, which is answer number 4. I see 86 answers for answer number 4, and not so many for the others. Okay, so, oh, now you see, now you can see it. And it turns out that the majority is correct, because if I show the correct answer, it is the 4th one. So indeed, the mem store is where you accumulate the new key values. When users do things in HBase, they delete, they insert, they update. So we just accumulate key values in the mem store, and then we flush them. The cache is something different. You know what a cache is, right? A cache is just a copy of something. It's just a copy in some medium that is faster to access, right? Like the CPU cache, level 1, level 2, and so on. And so it's a cache. And so what it caches are the key values that are in the H files already, right? And technically, it caches them in blocks. It's going to take entire H blocks from the H file and put them in the cache. You don't need to know details about the cache, just that it's a cache, but technically there's a level 1 and a level 2 cache, right? So there's already a lot of logic in there, but really don't worry too much about the caches. You just need to know that they're there and that the caches contain values already in H files, while the mem store is really the fresh ones that we are so scared to lose because of electricity shortage and for which we need a write-ahead lock. Who is comfortable with that? Right? Okay, so this is a good rehearsal. Speaking of H blocks, I think the next question is about the blocks. Let me see. Yes, so the next one is about another potential area of confusion, that oh, it doesn't project anymore. I'm going to put it back then. There you go. So what is the difference between the HDFS blocks and the HBase blocks? I call the HBase blocks H blocks. Answer number 1, they are the same. Answer number 2, H blocks have a default size, H blocks, the HBase blocks, that is more than 1,000 times that of HDFS blocks, right? So H blocks are much larger than HDFS blocks, the way it's typically configured. Answer number 3, multiple answers possible, right? Answer number 3, we say that HDFS blocks have a strict maximum size that you can absolutely not exceed. That's a strict limit, never is more than that, but the user can change it. While some H blocks can actually exceed the configured block size. So there's some elasticity in the H blocks, right? Answer number 4, HDFS blocks are created only considering bits. It's just zeros and ones, and then we count zeros and ones, and that's it, that's the block. While H blocks must contain full key values. It means that an H block is more logical and contains entire key values. You never split a key value across different H blocks. It's always fully in the same H block. Answer number 5, H blocks, unlike HDFS blocks, allow random access writes. You can randomly write into an H block in place. Answer number 6, H blocks are logical blocks within an HDFS file, which also contains an index of them. And I really mean within the file. So that's using HDFS, you store a file, and the contents of that file is logically made of H blocks in there, plus an index also in that HDFS file. That's the H file, by the way. And answer number 7, the H blocks are the physical blocks of the underlying disk used by HDFS. You know that when you have the disk on your laptop, the commercial disks, they have blocks on them, right? There's these 4 kilobyte blocks that in which you read and write from the local disk. And so that last statement says, these are the H blocks. These are the 4 kilobytes physical blocks on the disks that are sitting in the data center on the data nodes. So by now, I assume you pick. So basically, you just pick the ones that are correct, and you do not pick the ones that are incorrect. And now I'm going to try out if I can make your answers appear. So I can see them. Now, should appear anytime. Expectations, right? We expect it to happen anytime soon. Okay, well, technically, I see the numbers right here. It's just that the graph is not displayed. So based on the numbers, I can say a lot of people picked answer 3. A lot of people picked answer 4. less picked answer 5, then 6 has a lot of you picked it, and the last one is not very popular. So I think basically the majority got it correctly. Is there a way I can display, show the, that's strange, it doesn't allow me to show the correct answers. I think I just need to click here. So if I click, I just make them appear. Yes, okay. And now, just moving the mouse. Now you can see the correct answers. So basically you got it correct. The majority votes got them correct. So let's discuss. Well, first, the first answer, no, they're absolutely not the same. I mean, this is why I call them H blocks, precisely to make sure you understand these are not the same as the HDFS blocks. Answer number 2, why is it incorrect? H blocks do not have a default size more than 1,000 times that of HDFS blocks. Why is that incorrect? What are their default sizes? Yes? It's reversed, exactly. It's the opposite. The HDFS blocks are roughly 1,000 times larger than H blocks. Can you remind me what is the default HDFS block size? Anybody? Yes? Yes, 64 megabytes or 128 megabytes, perfectly fine. It's the order of magnitude, right? In Azure Blob Storage, they even push that to 4 gigabytes. But basically, that's the order of magnitude in HDFS. So typically, the value I give you is 128 megabytes. And what about the H blocks? How much? 64 what? Kilobytes, exactly, 64 kilobytes. So you see it's roughly 1,000 times less than an HDFS block, right? So yes, indeed, there is a factor of 1,000, but it's the other way around, right? Okay. Answer number 3, it is absolutely correct. For an HDFS block, when you arrive at 128 megabytes, it stops there strictly. You will not have a single bit more than that, right? Of course, the user can change the size, but whatever size the user puts, it's never going to exceed, right? Who remembers that? Okay, very good. So, but H blocks can exceed the configured H block size. Why? Do you remember why the H blocks can grow larger than the size? Yes? Exactly. If you have a key value that wouldn't be finished at 64 kilobytes, then you extend the H block until the end of that key value, right? So this is the correct answer. So the H blocks are elastic, and in fact, they can even grow to 10 megabytes if you have very large values, right? Like a big XML document or a big JSON document of 10 megabytes, then of course, the H block is going to extend to that. Okay, so yes, that's the correct answer. Number 4, HDFS blocks are indeed created only considering bits. An HDFS block is just zeros and ones, period. HDFS has absolutely no idea what you put in the files. HBase knows, but that's because it's the client. So this is the one that puts things in the files. But H blocks must contain full key values, right? Again, that's the idea. We wait until the end of the key value. So H blocks are a bit more logical than HDFS blocks because they really contain full key values. Okay. Number 5, H blocks allow random access rights. Why do they not allow random access rights? Yes? That is correct. So basically, you basically said that the way we write the H blocks, or more generally the H files, is append only. That's because of HDFS, right? HDFS is a system where you can just write files or append to HDFS. So this is why we don't have write random access in HDFS. If you ever try to have write random access or random write in HDFS, it will be super slow, super slow. So this is correct. Technically, the appending of key values would happen more for write-ahead logs. For the H files, we would just write them entirely, right? You just write the entire H files. But your answer is correct. That's the justification for batch processing. It's that we cannot have write random access on HDFS. Okay. So that's why the 5th one is incorrect. The 6th one, H blocks are logical blocks within an HDFS file, which also contains an index of them. That is correct, right? So now when you look at an H file, forget that it's HDFS. Forget the way it is physically stored. It's just a file like any other. A file is just a large sequence of bits logically, right? So it is a file that happens to be stored on HDFS. And in that file, we just organized on the logical layout of the file, the H file, we put the H blocks, one after the other. And there's more into the H file. There's also some indices and some metadata and so on. That's so complex that I didn't want to scare you with that. But among others, we have an index of the H blocks that we can load into memory. And that way we can access the H files and the H blocks in the H files efficiently. Okay, who is with me? Right, very good. And the last one, the H blocks are the physical blocks of the underlying disk used by HDFS. Why is that not correct? Yes? Exactly, they are not physical blocks. The physical blocks on your laptop, do you remember the size? It's 4 kilobytes, right? It can vary, of course, by operating systems, but roughly 4 kilobytes. And here we are talking about 64 kilobyte logical blocks that are just part of the logical layout of the H file. This is what they are. But this is not the same as the disk 4 kilobyte blocks that you access physically on the disks of the data center. Okay, who is comfortable with all of that? Okay, just wanted to rehearse, put it back in your memories, all of this accumulated knowledge. Very good. Do I have anything else? Oh, no, I don't have anything else. So before I move on to the next part, so now we are going to continue data modeling. Any questions? Yes, I see. Maybe we can use now this microphone. Yes. You see, Bojidar is very careful with the microphone. Yes.
One question regarding the quiz itself. Can it happen that a H file is stored on 2 different HDFS files? Like it's split, or does it is it taken into account that an H file is not split between 2 different HDFS files?
Do you mean HDFS blocks?
Yeah, HDFS blocks.
Yeah.
Or, yeah, HDFS block.
Absolutely. So it is indeed possible that an H file is made of multiple HDFS blocks. Because an H file technically could be, I think we tolerate typically up to 10 gigabytes large H files, right? I think when you start having H files more than 10 gigabytes, this is where you start splitting. You will start splitting the region, right? And if you do the math, 10 gigabytes is made of how many 128 megabyte blocks?
How many?
Yeah, divide 10 gigabytes by 128, small exercise. So I hear 8,000. I heard another answer. Did I hear 80? Who says 80? Yes, it is indeed 80, right? 128 megabytes times 8, that's 1 gigabyte, and times 10, that's 10 gigabytes, right? So 8 times 10. So 80, you can basically have as many as 80 HDFS blocks that constitutes an H file, right? But the way you should visualize this, imagine a very large H file made of multiple HDFS blocks. The way that these HDFS blocks are cut is totally unaware of the layout, because HDFS couldn't care less what there is inside. So you basically have whatever H blocks are in there and so on. HDFS doesn't care. HDFS counts 128 megabytes, bam, you cut, right? That's your first HDFS block, and then you continue. So it's totally unrelated to the H blocks. But it does mean that you might have an H block that doesn't end in an HDFS block, and you need to continue reading from the start of another HDFS block. That is absolutely possible. And it will typically happen for the very last H block that starts in an HDFS block. That's slightly inefficient, but luckily it doesn't happen all the time, right? Most of the H blocks are well within the same HDFS blocks. Once in a while, you will have one that is spread across 2. Right. Does it answer your question?
Yeah.
Yeah. Okay. Remember that, because we'll see it again in MapReduce that we have the same problem, that we have something that starts in an H block, in an HDFS blocks, and that doesn't end but continues in the next HDFS block, right? That really has to do with logical versus physical. That the HDFS blocks strictly cut at the number of bits that you have. All right, any other questions? Yes? Maybe the microphone, very small hops, multiple people in the middle. Oh, wow, directly. Yeah, okay.
I just wanted to ask about major and minor compactions. Could you explain to us when minor compactions happen and when major compactions happen? I think in the exercises you've given a description of what they mean, but I just want to understand when are they triggered.
Yep, okay. So minor compaction, major compaction. A minor compaction, basically, they happen kind of all the time. It's like a daemon in the background that just keeps finding H files to compact, right? So you have it running in the background. There is an algorithm that is not part of the material of the lecture, don't worry, but there is an algorithm that is meant to select candidate H files to merge, and then it merges them, it compacts them. So this is called a minor compaction. And basically, the algorithm tries to do it al dente, right? It tries to find a reasonable number of files that are not too big, they are not also too, like one very big, one very small, so it avoids that. So it selects a few H files. Typically, if you want to visualize it in your mind, typically between 3 and 10 H files, it's going to select of roughly similar size, and then it compacts them to a single H file. And then it does it again and again and again. So it's really just a daemon running in the background that keeps looking for H files that could be compacted, right? So there's an algorithm that does that. The effect of that algorithm is something that looks like the 2048 game that I showed you, but the 2048 game is only a visualization that is kind of an ideal thing that in the way they would be compacted. In reality, there's a bit of randomness because you just apply the algorithm. Oh, I'm going to compact these ones. I'm going to compact these ones. There's a bit of I would say non-determinism due to the way the system works, right? But you just have this daemon running in the background that looks for a few H files between 3 and 10 of similar size, and it compacts them and does it regularly. A major compaction happens much, much more rarely because that's a very, very heavy process. And once in a while, you might think, okay, now this is that has accumulated so much that you have multiple H files of multiple sizes. Now is the time to just merge them all into a single H file that has everything. That is a major compaction. This one is rarer. I can't remember, maybe we can look up the order of magnitude. Maybe I put it in a Moodle, but I think it's not even every day. It's maybe every week or something like this, right? And then you really take all the H files, all of them, and you create a single H file that contains all the data, right? So that is the difference between minor and major. They differ in the fact that minor is all the time in the background, major is rarely once in a while, right? There is another difference between minor and major is that a minor compaction doesn't modify the contents. It keeps the key values as they are and just put them in the merge H files. But in the major compaction, we actually use the opportunity to do a bit of cleanup, and we get rid of the old values or the superseded values, or when you delete it, you can get rid of completely of the deleted values. Otherwise, you just have this tombstone, right, that marks it as deleted. But when you do the major compaction, you see the tombstone, so you just remove everything of that key, right? So that's the second difference. For whom does that make sense? Right? Okay, but you know, this is already advanced, right? You're already pushing the boundary of knowledge here, right? So already that kind of knowledge is quite advanced, right? But this is very good that you try to understand it at such deeper level. Okay, I see another raised hands over there. Maybe you can, in small hops, transmit the microphone. Very ambitious, yes? Okay, go ahead.
I wanted to ask about the mem store, and is there a default size at which it usually flushes? And does it usually
when we
into
flush,
one H file?
I don't remember by heart. So I know 10 gigabytes is the size when we start splitting. I think it's a few megabytes. Let me see. If I can. I think it's around 10 megabytes. There's basically, it's a configuration parameter, right, that you can tweak as a user, and I'm just seeing if I find the default value. Oh, it's that's easy to remember. It's actually around 128 megabytes. That's kind of the size of an HDFS block, which is actually very clever if you think of this, that you basically wait until you have enough to fill an entire HDFS block, and then you avoid having something that's smaller than an HDFS block. So that's easy to remember, roughly the same as an HDFS block, right?
So it all flushes into one H file.
Yes, when the mem store reaches 128 megabytes, flush to an H file. That will be made of basically around one HDFS block.
I just wanted to confirm about random access, right? So when we say that it's not possible, it's slow, do we mean we cannot change a specific value, or we cannot change it in place?
In place.
In place.
Yeah. When we say random write access, we mean in terms of the file system, right? Typically, when you say random write access, you think of the file system, and so it means you cannot edit the H files in place. Because just imagine for a moment the thought experiment of that. You basically have an H file and you want to edit it. Do you see that you would need to basically locate where in the H file you want to add a key value? Then you would insert it, but it's sorted, right? So if you insert it, you would have to rewrite all of the rest of the file, all of the bits that follow, you need to rewrite it again and move them. So it's very intensive to do because it has to be sorted. Plus, if you would do that, that would also affect the size of the H blocks because you put it and then the H block is bigger. And then that might become unoptimal with the size of the H blocks. You will have very large H blocks that contain many key values and some less. So you would ideally have to resplit the H blocks and so on. But you see, this would be too complicated and computation intensive and resource intensive. So that I just told you that as a thought experiment. This is why we don't do it. This is why we don't attempt to modify the H files in place. It would both be very cumbersome to do and very inefficient because of all the latency and all the time that it would take to do it at every single update. Right. Yeah. Does it make sense?
Yeah, so we just add it as a new version, and this new version goes right ahead log, mem store. And
you just put it in the mem store, right? That's basically what happened. You put it in the mem store, that's very efficient. It's just a working memory access. You append it to the write ahead log also, but that is also efficient, right? Okay, very good. Any other questions? I don't see raised hands, but maybe Boji sees some, otherwise on the Zoom chat.
Yes.
Is there one? Yes, go ahead.
I had a question for your explanation for the last question. So basically that H blocks are logical blocks within HDFS files, but how I understood it would it be that they're more the logical blocks in H files, not HDFS. And HDFS wouldn't necessarily have those logical blocks, just the bytes.
Yes, I see. So here it's about the use of logical physical. So this is really just about the fact that we built a layer of technologies, right? And everything that is logical is physical actually to the upper technology, and it's logical to the lower technology. So everything is relative, right? It's everything is relative. So when I said the last answer, physical, I really meant as physical as it gets because you're talking about the physical drive that is on your machine, right? So that's the most physical, well, more physical than that is the molecular level, right? So this is really physical. Then you have the HDFS blocks, which technically would be logical with respect to the physical drive, right? But the HDFS blocks would be physical from the point of view of HBase, right? It always depends on the perspective with which you look at it, right? From the perspective of the drive, the HDFS blocks are logical. From the perspective of HBase, which uses HDFS, the blocks would be physical, the HDFS blocks. And so another way of saying that is that from the perspective of HDFS, the H blocks are logical because they come from above. They come from a user of HDFS that specifies a file layout that HDFS knows nothing about and that gets stored in that. This is why it's logical with respect to HDFS. So remember, everything is relative. What is logical, it's coming from above, physical from below, the physical interpretation. Every time you have a threshold or a data independence line somewhere, logical above it, physical below it, but you can have multiple data independence limits if you have a very complex system. Right. Did I answer your question? Yeah. Awesome. Well, we spent a full hour. That was great. So we'll have a break and then I'll continue on data models in the second hour. Right. Thank you very much.